This is a radar aerial, and it seems to be looking for something, doesn't it? How does it see an aircraft, for instance, hundreds of miles away and in the dark too? Well, later in this program, we shall be seeing more of radar. But first, here's something similar, but very much simpler, which is a crystal set. This is the simplest possible radio receiver, and you can easily make one yourselves. It has no mains connection or batteries, but it does need a good aerial and an earth. It makes rather a quiet sound. Where does this energy come from, and how does it get to the crystal set? I expect you're thinking the answer is something about waves, and you'd be right. This time we're going to talk about electromagnetic waves. These waves are involved in radio and television, also in radar and radio astronomy, and even in X-rays and in light. The trouble is that the wave motion, the motion itself, is too difficult to see. And even if we could somehow make it visible, the frequency is far too high for us to see the waves, even with a stroboscope. How then do we know that they are waves? Well, there is some evidence, and I hope you'll agree that it is fairly convincing evidence. Now, our crystal set receives waves which are about 500 meters long, far bigger than this studio. In fact, here's a football pitch drawn on the same scale. We couldn't possibly fit even one of these waves into the studio. Fortunately, we have an apparatus here which produces electromagnetic waves which are very much shorter than 500 meters. And they're called microwaves. This part of the apparatus sends out the waves, and it's called the transmitter. And we've labeled it T. The waves travel across here, and they'll even go through a vacuum until they're picked up by this part of the apparatus, which is called the receiver, and we've labeled it R. First, let me show you that waves travel from the transmitter to the receiver. Both of these have aerials on which are in the shape of horns, as I expect you can see. With the transmitter switched on, nothing is heard in the loudspeaker here until I aim the transmitter at the receiver. The loudspeaker here makes a note, a sound wave, whenever electromagnetic waves travel across to the receiver. But I don't want you to be confused between the sound waves coming out of here and the electromagnetic waves coming along here. So I'll disconnect this loudspeaker and use this meter instead. There, we get a steady meter reading as the waves reach the receiver. As we can't see these waves, let's look at some of the properties and see if we can recognize waves in this way. Sound waves and water waves we saw both went through gaps and to some extent round corners, and we call this diffraction. Let's see if it works with these microwaves. Here's a slit which I'll put in front of the transmitting aerial, and it's so wide, in fact, that it doesn't cover up the aerial at all. Now, the waves received will be registered on this meter, and we'll give you an enlarged picture of it. Straight ahead here, we get a reading of about 90. Round to this side, the reading falls off until it's about 10. And round on this side, it's down to about 15. In fact, the energy does fall off rapidly round the corners, as in this diagram. Now suppose I narrow down the slit. Where do you think the energy would go now? I want you to draw on your paper a narrower gap and sketch in some waves to show where you expect the energy to go, if we are right in thinking that these waves are diffracted. Draw big waves where there is a lot of energy, and small ones where there isn't much energy. Right, let's try it. Here the reading's about 30. Here it's down only to 20. And here it's 20 as well. So you should have got a diagram something like this, with less energy being given out straight ahead, but more spread out on either side. We seem to have got diffraction again, and some evidence of waves. Now, here's rather a different arrangement. I'm going to put the slit in front of the receiver, so that the receiver is looking through a narrow slit. It's what we call a narrow aperture. And now I'm going to use this receiver to find where the transmitter is, as a sort of telescope. Not a telescope for magnifying, but just for finding positions. Now, if I rotate this, the reading doesn't alter very much, and we'd have quite difficulty in finding out just where the transmitter was. In fact, it could be in any of these directions, and we've got an arrow on the receiver to show where it might be. Now, if I make the slit a bit wider, there, let's see what happens now. The reading's much bigger at the moment. It's about 90. And it falls off rapidly as I turn this receiver. To find out where the transmitter is, we naturally take the highest reading we get, which is about there. But still, it's not a very precise position. Now, do you remember the radar aerial? Well, it was something like this. It had a reflector. And this can be used, in effect, as a very wide aperture aerial, so that it reflects energy into the receiver aerial. And of course I must turn this round. And also take the slit away. Now we've got quite a big reading, and when we're looking for the transmitter, we really want to find where the maximum reading is. See, it falls off to 50 quite quickly on either side. And this seems to be the direction in which our transmitter is, and we get a very precise measurement of this with this wide aerial. And we say that this aerial has a much greater resolving power. Another property of sound waves and of water waves, which could hardly be explained unless these two motions were in fact wave motions, This was called interference. Two waves meeting seem either to add up and strengthen each other, or they can cancel out and make each other weaker. Here's a model to help you understand how this can happen. Here are two waves in step. Imagine they're moving along and they meet. The result is a much bigger wave. And now over here we have two similar waves, but they are out of step. When these two waves meet, we get no wave motion at all. So this wave would correspond to an increased motion, and this one to no motion at all. Here it is for sound waves on the field with the boys. These boys were standing where the sounds added up to produce a maximum sound, and there, and in between, the two waves from the loudspeakers almost cancelled out and produced a minimum sound. Here's the same pattern with two dippers vibrating in a ripple tank. Do you suppose this happens with microwaves? Well, here is our transmitter, and instead of having two dippers or two transmitters, we've got two gaps here. And the waves going through these two gaps will meet again at the receiver and give a reading on the meter. Now watch while I cover up one of these gaps. Cover up one gap and the meter reading goes up. Uncover it, cover it up, and uncover it. So here we have two wave motions apparently adding up to give nothing. If I move this round, we can find about here we've got a maximum, and then round here a minimum, where they cancel out. A bit further along we've got another maximum, and here's the minimum again. On the other side we get a minimum here, a bit further round there's a maximum. If I had time, I could move the receiver in and out and show you that this pattern produced lines roughly along here, and another one about here, and another one here. And here is a pattern with which you're probably getting familiar. Produced by waves coming through these two gaps, and the maxima are here, here, and here. And now I'm going to estimate the wavelength of these electromagnetic waves by comparing them with the shadows of the water waves on the ripple tank. I'll arrange these two gaps so that they're directly in the positions where the images of the slits are. And now I'll alter the wavelength of the ripples until the strong ripples occur more or less along these lines. They need to be a bit longer. That's about it. So we get strong disturbance of the water where these black lines are. Now I'll measure the wavelength of these ripples by marking it on this ruler. There, there, there. And you can see that these shadows are just about 3 centimeters long, just over. And so this pattern on the card is made by 2 gaps of the spacing I had before, with waves 3 centimeters long. And this is strong evidence that our microwaves are in fact 3 centimeter waves. And now you probably want to know how fast these waves go. Well, they go very fast, and it's rather a delicate measurement, which we can't do now. But you might like to jot down the answer. It is 3 times 10 to the 10th centimeters per second. 30,000 million centimeters every second. That's about 186,000 miles a second. And all electromagnetic waves go with about this speed. Now, at the beginning, I said we should see some more of radar. And radar is a very important thing, and it has many uses which you might like to think of. We are going to concentrate on its use for navigation. Throughout its flight towards an aerodrome, this aircraft can be watched by this rotating radar scanner, situated on a tower next to the radar control room. The scanner is beaming out pulses of energy, of electromagnetic waves. Some of the energy hits the aircraft and is reflected back to the aerial. Inside the control room, the operator watches the screen rather like your television screen. By suitable adjustments, he can see a bright spot approaching the center of the screen. The spot, of course, is a sort of picture of the aircraft's progress. Now the aircraft is almost overhead. What radar really does is to use the echo idea. The radar transmitter, which is a more powerful version of the one we have been using in the studio, sends out short bursts of waves. They are focused into a beam with this aerial and reflector, the scanner. If an aircraft comes within range, the scanner can be tilted towards it, and some energy is then reflected back from the aircraft. The scanner is also a receiver, so it picks up the echo and sends a signal to the cathode ray tube. Here is the scanner from above, with the cathode ray screen shown as well. As the pulses of waves travel out from the scanner, the spot travels across the screen. These waves, as you know, travel very fast, so that several hundred bursts go out every second. So it's as if we were sending out a beam, and this corresponds to a line on the screen. But as you know, the scanner turns, and the line on the screen turns with it. Now when an aeroplane comes within range and the beam intercepts it, a spot appears on the screen due to the echo. Notice that the position of the spot on the screen and its distance from the center corresponds to the position of the aircraft and its distance from the center. We've made a model to summarize what is happening. This is a large-scale version of the screen, which is, of course, inside the building. See how the scanner and the line on the screen turn together, and how, when an aircraft appears, the spot, due to the echo, travels across the screen. And now it's time for you to note the questions. Remembering that this is the speed of electromagnetic waves, what is the frequency of 3 centimeter waves? And the second question is about the film we're finishing with. It concerns ship's radar. Here is a scanner on the ship, a rotating aerial. And below it is the radar control room. And here is the screen on the cathode ray tube. The question is, what do you think is being shown on this screen?